Yasamin, are you here?
Hello, yes.
Okay, then could you share your screen?
Sure.
Okay, then let us restart the session. The next speaker is Professor Yasamin Jalalian. Am I right? Pronunciation is okay, correct?
I'm not a professor, I'm a graduate student, but other than that, it's all right.
Speaker is Professor Jalalian. Okay, from California Institute of Technology. The title of our talk is Forecasting Hamiltonian Dynamics with Computational Graph Completion. So you have 25 minutes, including discussion. So yes, please.
Thanks for the invite. I'm happy to be here. Today I'm going to talk about forecasting Hamiltonian dynamics with computational graph completion. Okay, so the way I'm going to go through this talk is that I'm first going to motivate a little bit why we consider data-driven methods for studying dynamical systems at all. Then I'm going to talk about kernel methods in particular among those data-driven methods, because that's going to be the underlying framework of our main methodology. Then I'm going to talk about computational graph completion in particular, which is our main framework for studying Hamiltonians. And then I'm going to show you some numerical results, which are at a preliminary stage at this point, because this is a joint work with Boumediene Hamzi and Hénon-Heiles and some other collaborators at Caltech. And our results are still in progress. I mean, the numerics of this work is still in progress. Okay, so I'm going to start with some motivations about why we consider data-driven methods for dynamical systems. So a little bit of history. Dynamical systems have been around since Newtonian mechanics. Their origins go back to Newtonian mechanics, and it was in 1890s that Poincaré founded the rigorous mathematical foundations for it, with the goal of it being to study properties of these systems without having to solve the differential equations analytically. And a little bit afterwards, again in 1890s, Lyapunov also developed some approximation methods to define stability of sets of ODEs. And since for most of dynamical systems, they are not analytically tractable to solve, there was this emergence of classical numerical methods. These numerical methods are based on the mathematical theory. However, they are limited to known models, and they are also computationally expensive in high dimensions. And this is why more and more people are considering data-driven methods. These methods have the advantage of being able of allowing us to analyze high-dimensional unknown models like climate models purely based on data. However, the theory of how most of these methods work is still underdeveloped. Now, the main two approaches to study dynamical systems with data-driven methods are neural network-based methods and kernel-based methods. For the purpose of this work, we are only considering kernel-based methods as they have some advantages over neural net-based methods. First of all, they're theoretically more well-founded. They're also interpretable and amenable to numerical analysis. Moreover, the number of kernel parameters to learn is significantly smaller in most cases than the number of hyperparameters that somebody would need to tune for neural networks. They also come with rigorous error estimates, and there exist efficient polylog linear methods for inverting kernel matrices, which allows dealing with a large amount of data in a computationally fast way. Okay, so to set up some notations and to say why we are particularly working on Hamiltonian systems. So Hamiltonian systems arise everywhere in physics, from quantum mechanics to statistical mechanics and continuum mechanics. Okay, and they also have a particular structure. So as you can see, the derivative of P with respect to time is the partial of H minus partial of H with respect to Q, and the derivative of Q with respect to time is partial of H with respect to P. And so they're conservative systems, and we are hoping that by using this particular structure of Hamiltonian systems, we would be able to forecast them for a further period of time than a general dynamical system. I should say that in these equations, so the Q is a function of T, which represents the generalized position. P is a function of T, which represents the generalized momentum. And so our data is a finite set of points on Q and P. So we don't know P and Q outside this finite set of time series. And then our goal is to just learn this Hamiltonian and predict the system further in time. Okay, now I'm going to talk about the basics of kernel methods and the theory of kernels that we would need to know in order to understand the theory of the underlying method that we're going to implement. Okay, so I'm going to start with the very basics. A positive definite kernel on a set X, which can be any set, is a function that is that goes from X cross X to R and is symmetric. And also the kernel matrix of this kernel function is a positive semi-definite. Which by the kernel matrix, what I mean is that it's a matrix that its ij component is the kernel at xi and xj, and it's explicitly written as explicitly written here. It just means that the kernel matrix is positive semi-definite. So in that case, we just call our kernel positive definite. Now, there's an important result that goes back to 1950. So again, we're going to assume that X is just any set, then the function K is a positive definite kernel if and only if there exists a Hilbert space H and a mapping phi from X to H, such that the kernel at X and X prime is just the inner product of this mapping evaluated at X and at X prime in the Hilbert space H. And now this is important because in practice, what one would always want is to, so this phi is just a feature map, and this H space is going to be the feature space. And what one would want is that if, for instance, in the data set, if our data is not linearly separable, we want to find a feature map that would map our data to another space. And then we would want our data to be linearly separable in that other space. And the next theorem is going to provide us, so here, so far, our feature map is not unique. Let's proceed to the next definition. So we're going to assume that X is a set and H endowed with an inner product is the Hilbert space whose elements are the functionals on X. Then the function K is called a reproducing kernel if H contains all functions of the form Kx, which map T to the kernel of X and T for all X. And if for every X and F, the following property, which is called the reproducing property, holds, which basically says that F at any X would be can be represented as the inner product in the Hilbert space of F and Kx. And now if a reproducing kernel exists, then H is called a reproducing kernel Hilbert space. So now we have this mapping of the data in X to a high dimensional Hilbert space H through this feature map Kx. And now in H, we can consider just simple linear models, Fx being just the inner product by the reproducing property that I just said. And now here we also have the uniqueness. So if H is an RKHS, then it has a unique reproducing kernel. And conversely, a function K can be the reproducing kernel of at most one RKHS. And this theorem now allows us to refer to the reproducing kernel of an RKHS and the RKHS of a kernel. And finally, last but not least, just a remark, positive definite kernel is equivalent to reproducing kernel, so we can just refer to it as a kernel. Okay, now I'm going to state why we needed all this theory, because what we are considering in practice is that we have a training data set and we want to learn a prediction function F, mapping from a set X to Y. This could be the Hamiltonian, for example, in our case. Now, equivalently, we want to find the minimizer of the empirical risk of the following empirical risk, where here L is a loss function and lambda is the regularization parameter. And we can find this minimizer by this theorem. So this is the representer theorem. And it's basically telling us that the minimizer of a problem similar to the problem before is going to be, it's going to always admit a representation of the form of linear combinations of the kxi's, for xi's being the points of our data set. And so this now allows us to find a representation with respect to the kernel that we have for the best approximation of our unknown function. More precisely, so with the squared error loss, using the previous representer theorem, we're going to have the following interpolant for our F, where here, so F of X is going to be the K of little x and capital X times the inverse of the K of capital X and capital X plus lambda times the identity matrix times Y, where X is the vector of our xi's, Y is the vector of yi's. So these are the data. And then, and this X, by the way, can be any X. The little x here, and then the K of capital X and capital X is just the n by n matrix with entries K of xi and xj, and finally the K of little x and capital X is the n vector with entries K of x and xi. And so with having said all of this, now we are ready to move to the main framework of what we are using in this work, which is the computational graph completion. So precisely, considering that we have a general computational problem with some unknown variables, this approach suggests that we can model our computational problem as a computational graph in a way that we would represent our variables of the computational problem as the vertices of the graph. And this graph is directed, and we will also represent the functional dependencies between the variables with these directed edges. This here on the right is the graph corresponding to the Hamiltonian system. I'm going to precisely say what each component represents. So this is just for all the computational graph completion framework graphs. We represent the square nodes to be our primary variables, the round nodes to be our aggregated variables. The blue nodes are the noise variables. Even if our data isn't noisy, we might want to add some noise variables to the system for different purposes. In case of model misspecification, this would help with the misspecification, and also it will help with numerical stability. And so now the edges, if there is a directed edge from vertex x to y, it means that y is a function of x. If in particular this edge is black, it's a known edge, and if it's red, it's going to be an unknown function. It's going to represent an unknown function. And finally, if there are two directed graphs going from two different variables to another variable, and all of them are square variables, then it means that this is a sum of a function of the first one and a function of the second one. So more precisely, in what this would translate to the case of our Hamiltonian. So we have the t variable, which is our time variable here, with two, which has two outcoming directed edges that are red, which represent Q and P. This goes to Q and Q dot and P dot. At this point of our numerics, we're just assuming that we don't have any data on the Q dot and P dot themselves, but we're just deriving Q dot and P dot to be the derivatives of our interpolants. And then they also, here, the P and Q, they aggregate to the Q and P. And then with this unknown function H, we have the Hamiltonian, and these are our noise variables in this graph. So the approach is simple. So in terms of what I presented, we basically replaced the unknown edges with kernel ridge regression formula that was in the previous slides. And so there's a connection between this and instead of the kernel ridge regression, we can say that we're fitting Gaussian processes to, we're replacing our unknown variables by Gaussian processes. And then we compute their map estimators. For the purpose of this talk, I didn't get to the technicalities of this, but you can read this in the main work, which is computational graph completion by Hénon-Heiles. So just a remark, the main optimal recovery, the main optimization problem for the Hamiltonian case is same as before. So we want to minimize here the RKHS norms of the unknown functions, plus the regularization term here, subject to these constraints that are the constraints that are imposed by the Hamiltonian dynamic. And we would, with some manipulations and introducing some optimizations like variables, we would reduce this to an unconstrained optimization problem and solve it numerically to find the desired P, Q, and H. So now I'm going to talk in particular about two examples. and the results that we have so far for them. The first one is a 2-mass 3-spring system in which there's 2 masses and 3 springs attached to them, and the end of the springs are fixed. What we're doing is that we solve the system up to time 10 with classical numerical methods, and like this, we obtain 1,000 data points. And then we just apply this method that I explained numerically to it. And for the 2-mass 3-spring system, we can see that our prediction is completely equal to the truth. I still don't have precise error measures. But as you can see, you can't even see the true value. It's completely fitting the truth value. Our prediction is very accurate in this case. Now, the second example is Hénon-Heiles system example, which models nonlinear motion of a star around a galactic center. So what is going on here is that we do the exact same thing. So we just numerically solve it up to time 10. We just numerically solve it up to time 10, then we get 1,000 points and 1,000 data points, and we apply the same methodology. And here we don't have the exact accurate approximation. It still fits pretty well. Our prediction approximates the true value pretty well. So some possible directions could be using some more complex kernels, because at the current stage we're just using some Gaussian kernels to fit and see like how they would approximate, how well they would approximate. This has been done in some recent work by Boumedi and Hamzi, and it seems like they approximate pretty well. And I should note something on these plots that so basically until time 10 here, what we have is just the training set, but everything afterwards is going to be whatever we have forecasted. It's going to be the exact same thing here. But again, as we can compare, so here, even until time 320, we still have a pretty accurate approximation. But for the Hénon-Heiles case, especially for Q1 and P1, we can see that they're not as accurate, even until time 80. But yeah, so this is the current stage of the numerics. Thanks for your attention. And that would be it. I would be happy if there are some questions.
Thank you very much, Yasamin. Yes, so Jan Pablo, JP. Yeah, we cannot hear you. I don't know why.
Now it should be good.
Now we can.
Yasamin, yes, thanks a lot for the talk. Look, 2 quick questions. So the first one is there any structure preserving built into the algorithm? So what I'm trying to say is that if you neglect the fact that you have committed an estimation error in the Hamiltonian, ultimately what you end up having here is a discretization of Hamilton's equations. Is this discretization preserving either simplicity, variational structure, energy? Is there any of those things that is preserved by construction?
So as I showed, as you can see that it's predicting very well, especially for example, the example of 2-mass 3-spring is predicting very well the the values obtained from the classical numerical methods. So I'm assuming that it should be preserving the energy.
But one thing is the empirical the performance of what you are doing. But you see, studying your PhD in the place where you are studying, this is the place where all these techniques were developed. So you see, you have all these variational integrators developed in time by Jerry Marsden and company. And there, the goal of the entire design was to make sure that by construction, any of these structures was preserved. Some of these structures were preserved. You cannot preserve them all at the same time. So would there be a way to design this, well, this algorithm that you showed to us so that some of these things are preserved somehow?
Yeah, if you don't mind, can I jump in?
Go ahead, Madian.
So for now, I know what you are getting at. I mean, we still didn't do it yet, but as she said, I mean, we used only a Gaussian kernel. The next step is to use a kernel that preserves the Hamiltonian structure by design. I mean, this is something. We still didn't do it. Yeah. So to answer your question, we are still not there yet. So for now, we just want to use a generic kernel, and eventually, in the next step, to say, look, I mean, this is what we reached, but now we want to design a kernel that preserves the structure, and then that like a sort of in the same spirit as equivalent kernels. Here we would have like a structure preserving kernel by design. So the base kernel would satisfy what you want, but it's still not done yet. So yeah.
Very good. That's a great problem. So yeah. No, thanks a lot for the talk.
Yeah, I have the question.
Okay.
What happens if the kernel is negative definite? You have told here the kernel is positive definite, but if the kernel is negative definite, then what will happen?
It can't be negative definite. I mean, so by definition, we use positive definite kernels. Yeah.
Oh yeah. The evaluation mapping that you have mentioned here, is it always linear or non-linear? The phi t that you have, the feature map.
I see. I mean, it can be non-linear.
Okay, thanks.
Okay.
Hello, I have a quick question. I just want to check what is the relation between this kernel trick and the graph completion? Because I didn't see it super clear yet. Thanks.
Right. So the main approach of computational graph completion is to just provide a framework for modeling all the problems. So essentially what we're using is that to replace in the computational graph completion, we replace these unknowns with the kernel ridge regression. Did I
see, thanks. It's like embedding this ridge regression into the framework of graph completion, right? Am I understanding correctly?
Pretty much, yes.
Yeah, thanks.
Yeah.
Can I add something, or?
Yeah, there are other questions, but maybe later you can discuss directly.
Okay.
Yeah, I have a question. Am I audible?
Yeah, so can you ask later?
Oh yeah, okay.
On chat.
Sure.
Directly. Okay, then let's move on to the next speaker. Jun